Hi, in this video I'll be going through Unit 1 Edexcel Physics Mechanics ISP Task 3. So in ISP Task 3 we're going through the idea of trigonometry and resolving vectors, which will be covered a lot more in the last ISP task, in the next ISP task, but definitely Newton's 3 laws and their applications. So let's jump straight to the explaining everything tasks. There we go. Okay, so we've got the ideas of using Newton's 3 laws to explain how a ball bounces, or describe a situation of a bouncing ball. So remember the 3 laws. The first law is that an object will remain at rest unless there is any external forces acting on it. So a quick way of sort of simplifying that for thought is that if the resultant force is equal to 0, then acceleration is equal to 0, and if the resultant force is greater than or less than 0, then acceleration is greater than or less than 0. Okay, so that's the idea. Okay, so greater than or less than in those situations. But if it's equal to 0, then the acceleration must be equal to 0. So that's Newton's first law. Okay, that is also sort of expressed in Newton's second law, which shows that F equals ma, or F equals m change in v over t, which can also be written as mv minus mu over t, which you might remember from GCSE is change in momentum over time. But that there and possibly that there are the main two ways in which we cover it in AS Physics. These can mainly into A2. And third law is the law of equal and opposite forces. Okay, so remember, if objects, the best example is that of an apple, okay, on a table. So if object A, i.e. the apple, exerts a force on this very small table, onto the table, and the table exerts the same size force back onto the apple, but in the opposite direction. So remember, there's similarities and then there's differences in this third law pair situation. The similarities are the same type of force, same size of force, same duration of force, and it's the same line of action. However, they act on different objects and they act in different directions. Okay, so there's your similarity and differences for third law pairs. So now let's apply it to a bouncing ball. Okay, I won't draw the whole idea out. So you've got to use these ideas to explain what's actually happening with a bouncing ball. The idea is that at the start, when you drop a bouncing ball, the first law comes into play in the sense of there is a resultant force, i.e. the weight of the ball, that's pulling it down. So therefore it accelerates. So that's how the first law applies to the start of the situation. The reason why it bounces is because it comes into contact with the table. Okay, and when it comes into contact with the table, it applies a force on the table, the ball applies a force on the table, so the table applies an equal and opposite force back onto the ball. That means that it bounces. The amount of acceleration it feels can be calculated from F equals ma. If you rearrange for A, so F over m, you can figure out the acceleration it actually has. But remember, there's a resistive force acting against this from air resistance and also from energy loss during in the table. Okay, so that's why it doesn't reach as high each time around. Okay, so we've gone through just a quick situation there of where it just drops, and after one bounce of each of the 3 laws is applied there. Feel free to go into more detail if you wish, but that's a sort of basic core understanding that you need of that situation. With that in mind, let's get straight on to the questions for task 3. Okay, so lots of tables in these questions to try and understand what's going on step by step. Lots of diagrams, definitely. So, complete the statement of Newton's third law. Okay, so if body A exerts a force on body B, then body B exerts an equal sized force in opposite direction on body A. Straightforward. Okay, so table below, just as discussing, for each force, there's a corresponding force in Newton's third law pair force. In each case, it states the body that the Newton's third law pair acts on, type of force, and a direction. Okay, so the weight of the potatoes. The body that the Newton's third law pair acts on is what we're going to put in over there. The type of force needs to be over here, and the direction, okay, of the Newton's third law force needs to go in here. So if one is acting down, the other one's acting up. Okay, so to push the man on the ground, exactly the same sort of idea. So we've got to think about if it's the weight of the potatoes, and it's going to be the opposite way around for the other one. So for the push of the man, it's going to be the opposite way around for these for this one over here. So let me show you the mark scheme so quickly get through these table questions and get on to the wordier ones that are trickier to get a head around. Let's get the right one up. Okay, so equal and opposite force. Okay, so these are the trickier ones to get your head around. Yeah, these are pretty straightforward. Okay, so if the weight is from potatoes, then it's earth is the equal and opposite force. It's gravitational force, so not gravity. Remember, you can't use gravity as the name of the force. It's gravitational. So if the weight is acting down, there's going to be upward force afterwards. So the pushing around the ground. Okay, so the ground is what it's acting on, and it's going to be a downward force. So one of the marks for each of the columns. It's going to be a push for the type of force, essentially involving it, or contact force you could put. So I don't know why that's been deleted from here by accident. So push or contact force would have been fine. Okay. Oh no, sorry, they already put it in there, contact force. There we go. That's the reason why that was blank. Apologies for that. So, state Newton's first law of motion. Okay, so an object remains at rest unless there is a resultant force acting upon it. So there is no acceleration unless there is a resultant force. That's the idea. So the mark comes from linking the idea that a resultant force is required to the idea that that causes an acceleration. In everyday situations, it does not seem that a force is needed to keep an object, for example, the shopping trolley, moving at constant speed in a straight line. Explain why. Well, it's also the idea of resistive forces, and the fact that resistive forces are small. If they're small, then it just seems like things can be rolling on forever. So it seems like they're actually not required of forces. The fact that there are resistive forces. So what we're constantly having to battle against are these resistive forces. So that's what it seems that a force is needed to keep things moving. If there were no resistive forces, then things would just carry on going in a straight line. So think about an ice skater. They don't need to push off the ice again. They just keep skating on forever. Or think of a rocket in space. If it fired off, it just carry on at a constant speed because there are no resistive forces. The vertical forces acting on the trolley are in equilibrium. Explain what we mean by equilibrium. So no resultant force. That's what equilibrium means. The weight of the trolley in one of the Newton's third law force pair. Okay, so the weight is one of them. Okay, identify the other force in the pair acts upon. Okay, and what the type of force is. So the weight is so the weight of the trolley is one of the Newton's third law pair. Identify what the other force in this pair acts upon. So the other force acts on the trolley. And what type of force it is? Well, it's going to be gravitational because the weight acts onto the ground, so there must be a force acting back up. Okay, and a force acting back up is the gravitational force from the earth, or from the ground, is the way to put it. Right, give two reasons why normal contact forces do not form the Newton's third law pair. Let's check the previous answers first, and then I'll go through that in the mark scheme, because it's difficult to describe that, but the mark scheme makes it very specific what they're actually after. Okay. So let's get this page down. Okay, so got the idea of uniform or constant velocity in a straight line unless there's an external force or resultant force. Yeah, air resistance, mentioned that. Resultant force is 0. Okay, that's exactly what we said. So from the earth, gravitational force, exactly what we said. Okay, they don't act in a straight line. Okay, or they do not act from the same point. They act on the same body. Okay, so if they're from the same body, they can't be Newton's third law pair. Okay, they act in the same direction, and they are of different magnitudes. So remember, we've got to go back to this table. So why the normal contact forces are not Newton's third law pair is you're going back to this table and linking it all together. Okay, so that's what they're after in that question. 12. So the forces are talking about, by the way, if I just show you, are these two forces. Okay, they're not a Newton's third law pair because they're because of all the reasons. Although they're the same type of force, they're probably going to be different sizes. The line of action is completely different. They act on the same object and they're acting in the same direction, which means they cannot be a Newton's third law pair. Right. Okay. So a man standing on the earth, got a free body force diagram to see the forces acting on it. So that's the forces acting on the man, B and A, and that's the forces acting on the earth, C and D. Force A can be described as the earth pulling the man down with a gravitational force. Okay, so A is the earth pulling the man down with a gravitational force. Okay, use a similar form of words to describe force C, which forms a Newton's third law pair with A. So if it's third law pair, you can just replace the wording. So think about object A and object B again. So C must be the man pulling the earth up with gravitational force. Okay, so opposite direction, same type of force. Noting that force A and C are Newton's third law pair, write down three differences and three similarities and two differences between these forces. Boom, straightforward over here. Let's work through those again. So similarities: type of force, size of force, duration of force, or line of action of force. Differences: different objects, different directions. Which two forces show whether or not the man is at equilibrium? Okay, so we just want the forces acting on the man at that point. So that's A and B, or B and A, whichever way around you put them. Child is crouching at rest on the ground. Okay, so you've got some forces acting on the child. So A is acting from the child onto the ground. B is acting from the ground onto the child. D is acting onto the earth, and C is acting onto the child. Okay, so complete the following table describing forces A, B, and C. Okay, so if A is the gravitational force of the earth on the child, so A is a gravitational force of the earth on the child, then C must be the gravitational force of the child on the earth. Okay, so it's acting on you can see it's from the other body, it's acting on a different body, and you can see that it's acting in a different direction. So A and C are pairing up, so that means B and D must be pairing up. Okay, so we're talking about contact forces there for B and D. So B is a contact force from the earth onto the child. Why are the forces of A and B equal in magnitude? Because they're equilibrium. I think this has been mentioned already. They're standing still. Is at rest, because he's at rest, or because I think the best way to say it would be because he is at rest. And why must forces B and D be in equal magnitude? Because again, the Earth's at rest as well. Well, the Earth's at rest in relative to the child. Okay, so let's just compare. Let's just have a look at the table. There we go. Okay, so Earth gravitational upwards. No, wrong question. Okay, so gravitational Earth child contact force. Earth child, just like we said, and gravitational child Earth. Okay, because he's at rest or equilibrium, just like we said, or you could say for the fact that they're a third Lord's pair, for the second one. Okay. Oh, we didn't mention this one. What must the I'll scroll up so you can see it. What must the child do to jump, and why he moves upwards? Okay, so he's got to push down because D's got to increase, which is going to make him rise essentially. Because D is directly related to B. D and B are Newton's third law pair, just like A and C are. So therefore, if D was to increase, B would increase, and therefore would lift off the ground. Needs to get greater than A essentially. So he needs to get greater than the gravitational force pulling him down. Right. So 14, which is the last part. Again, another table. So what I'll do is we'll talk through the situation, we'll go through the mark scheme, and go through the table because it will clearly lay it out in there. So you've got figure 1 shows a box resting on the floor of a stationary lift. These are always tricky questions, and literally and honestly questions that I hate. These ones, I really dislike these, and I think they're very, very tricky, and they're notoriously poorly answered by students. So, for each of the following situations, tick the appropriate box to show the magnitude of the forces of A and B change, if at all, compared with when the lift is stationary. Okay, so here's our free body force diagram, and the diagram showing the forces A and B that act on the box. Okay, so A acting with B acting down. Okay. You've got to remember, that's what it's like when it's at equilibrium. Okay? If, so in other words, when it's stationary. If it's going at a constant speed, the force will be exactly the same as when it's stationary. Okay, so lift moving upwards at a constant speed, no change, no change. Okay, lift moving downward at a constant speed, no change, no change. It's only when it's accelerating, okay, are some of these forces going to be larger. Okay, and you've got to think about which force can be larger and which force can be smaller. Remember, B is acting down and A is acting up. Okay, so just like no change, just like I said. So remember, A is going to increase, So we've got an increase and a decreases in the columns over here. So how forces A and B change. So force B, for ticking no change in all 4 boxes. So force B will never change. If you look at force B, you've got to think about what it actually is. Let's go back to it. Force B is the weight of the object. Okay, so it's the weight of the lift. The weight of that lift will not change if we're assuming there's nothing inside of it, we're not adding anything inside of it, which is essentially what the situation is saying. So none of these will change whatsoever. However, A will change, and that will affect whether it's going to go up or down. So if A increases, it will go up. Okay, if A decreases, okay, then it will go down. Okay, so literally straightforward as that. Okay, so that one there, that one there, that one there, that one there, and all of these are no change. That sums up task 3 of ISP on mechanics, AS physics, for Edexcel. Thank you very much for listening, guys. Next time we're moving on to statics, which is going to involve a bit of trigonometry. So make sure that for next time round you're very hot on your trig, so we can go through those questions very quickly. Thank you very much for listening, guys.